So far, we have started 3 important chapters. In chapter 1, we started the claim frequency. In chapter 2, we started the claim severity. In chapter 3, we started the aggregate loss. So those 3 chapters somehow form the fundamentals of non-life actuarial mathematics. So in this video, I'm going to do a rather brief summary of what we have studied so far on those 3 chapters. Let's begin with the first one. So it's claim frequency. Okay, and we use N to denote frequency. So basically the meaning of N is the number of claims. Of course, depending on the subject of our study, sometimes it can be the number of claims for a particular policy or for a pool of policies. Since we use N to model the number, so it should take integer values, right? So as such, N takes integer values, okay? And here we have 2 cases. So let me say, so either N equals 0, 1, 2, all the way to a small number N, which can be, let's say, the cap of your risk pool, or N from 0, 1, 2 goes to infinity. Okay, there are several examples, right? We studied, for instance, binomial, okay? And we have our usual notation that is, for binomial, we use N it's a 2-parameter family, right? Small n denotes the total number. Okay, let me go back to our usual color. So small n, what you can think of is, okay, so I think n is the total number of policies. Okay, and for each policy is either no claim or 1 claim. Of course, this is a simplified setup of the real case, right? Because a policy can result in multiple claims, or what you can think of is either no claim or there is a claim or more than 1 claim, right? So it's either 0 or greater than or equal to 1, and we put everything non-zero to be in 1 category, and that is the probability of theta. Theta means the probability of, let's say, 1 claim. Okay, of course, for a policy, right, with this setup, a binomial distribution exactly captures the total number of policies that result in claims, right? Exactly the purpose of claim frequency capital N, right? So that is the first example. And another famous example is Poisson. So in this case, what you can think of is, assume the risk pool is fixed. Let's say, assume I run an insurance company. I know the number of policies I underwrote. Let's say it's a fixed number, say 10,000 policies. That number does not change. Again, it's a simplified setup, but it's probably the case if my company is big enough and I study the policy for a particular area. Usually, my pool of customers is somehow stable. So in that case, I can assume the total number is somehow stable, a fixed number. And according to my past experience, my N is the average of claims. Of course, number of claims, let's say from the previous history. And then I can set up a Poisson distribution to model the claim numbers for the next period. right? So I use historical information to give me an estimate for this intensity. Intensity, we know this is the mean, right? It is also the variance, but we try to use a lower moment for estimation. We know for a Poisson distribution, it is a one parameter family. The only parameter we need is the expected value or expectation. One way to estimate this lambda is to use the historical claims, and the average would be a nice estimator for lambda. And then I build this model for future. Right? The way or the reason why we need a model is because we want to forecast. Right? We don't want to look backwards to see what happened. Right? That's the for that point we don't need modeling. We have all the detailed data. So we want to do the forecasting. So here is the purpose. Right? Again, in this case, we use N to model the number of claims for this fixed risk pool. Right? Of course, there are many possibilities like a negative binomial, right, and geometric. We already discussed the meaning. For instance, for geometric is a weighting distribution, right? This is how you can basically understand the probability function better, right? So if we for a brief moment deviate from actuarial science, let's think of geometric distribution. In our textbook, we use geometric distribution to model the number of failures before the first success. So this is number of failures before the first success. Okay, negative binomial is a generalization of geometric, right? What you can think of is the same number of failures before the R's success. Which means if you set R to be 1, it's exactly the same as geometric distribution. Okay, those are the AB0 class. Okay, those 4 examples. We have 4 distributions. These are the most important things you need to know from chapter 1. Okay, for chapter 2, what we study is claim severity, and the notation we use is X. Okay, obviously a quick thing is X has to be greater than or equal to 0 because it's claim severity, right? And usually we apply a continuous distribution to model X. Okay, the reason is because the size can really be any number, right? So if there's a car accident, the cost can be $200, can be $200.20, right? Because there's a tax. So and some of the price of parts are really quoted in decimals, right? For example, a specific part could cost $99.99, right? It's not exactly 100. So the number can be really anything. That's why we usually prefer to use a continuous distribution to model the claim size. There are many choices, right? The easiest one would be exponential. Okay, and we have also studied things that are more complicated, like a gamma distribution, Pareto distribution, right, and the Weibull distribution, and many more. Later on, we can, what we usually see, those are somehow exponential family. Okay, obviously exponential family includes the very special exponential distributions. It also includes more, right? So we have many choices to model the claim frequency, the claim severity, excuse me. So we study something similar. We need to know the for each one of them, we should know the PDF. We need to know the expectation. We need to know the variance, and possibly the moment generating function. Those help us understand the characteristics of these distributions. But in chapter 2, something more important is the modification, right? We studied modification down here. Let's see, we have modifications on. So usually, you know, in this chapter, it is on each policy. Okay. The first one is deductible. D, of course, we usually set D to be strictly greater than 0. So this case is likely the most important one, and we often encounter a deductible in pretty much all short-term insurance, like auto insurance, home insurance, property insurance, you know, etc. So you start up with X. X is the ground up. Let X be the ground up loss. That means it's the original size of a loss, of an accident, of a claim, and XL. So this is my notation. So let me leave some space. Let XL be the payment in a loss event. Okay. So here my notation is this is usually, you know, when you use text, latex, that is the notation, right? You put a lower hyphen and put an L. That means it's a subscript. XL be the payment in a loss event. Okay. So by that definition, we have taking the positive. Sometimes I might write this positive sign as the superscript. Okay, so both are normal. Actually, writing a superscript is more often in mathematics. So this part is very trivial, right? It's very simple mathematics to separate this into two pieces. As you can see, once you introduce a deductible, what you cause is actually a probability mass down here, right? So our XL will be a mixed. It's a mixed random variable, right? With probability mass at 0. Okay, and we can easily calculate the probability at 0 is the CDF of your original loss at D. So even though, you know, we often apply a continuous distribution to model X, our XL would be a mixed random variable with a discrete point at 0, and the probability, well, we can easily derive, right? Okay, and from here we can also get the PDF. Oh, it's not exactly PDF, it's PF PDF of XL, right? So we already derived, so you should know how to compute this. A very useful formula is this. So this is a very useful formula. It often helps simplify the computation. So obviously, this Sx is the survival function. Survival function of X, right? This is a useful formula because for many of the distributions we have, in particular, exponential and Pareto, the survival function is in a nice form, right? You can easily integrate to actually calculate this integral. So that is the first modification. The second one is, from here, I should also introduce another one. Is for the same setup, X is the ground up loss. Now let XP, capital P, let me leave some space, be the payment in a payment event. Okay, obviously the difference now is it's not a loss event, it's actually a payment event. Because it is a payment event, so you will need to exclude those in the end get you 0, like the point here. Because now we are standing at the viewpoint of an insurance company. So if the original loss, big X, is less than D, something happened, but since the size is smaller than the deductible, the customer needs to pay out the entire loss X. The insurance company doesn't need to take care of anything. This is not a payment event to the insurance company, right? So in this case, if we consider the payment event, you will need to make this condition, right? Only when the ground up loss is bigger than the deductible, the insurance company will need to kick in to take care of some of the additional payments, and the additional payments would be the difference between the original loss and the deductible. So here is the XP. P stands for the payment event, and previously we have XL. L stands for a loss event. So here a huge thing is you always need to take care of the conditional probability down here. Please remember to divide by this guy. So you always need to divide by it, okay? So, and another big difference is XL is greater than or equal to 0, but XP is strictly greater than 0. Okay, that's because we only take care about, if you represent the insurance company, right, you only care about the positive payment to the company, right? So this is XP. For that, you need to derive the PDF of XP. Okay, often this is a continuous random variable. Okay, because we don't have the discrete point, right? We exclude it. You need to know how to derive this PDF, right? You can apply whatever the method you would like to use. You see, I usually start with the definition, right? The second one is policy limit. So the second one is policy limit. And we use U to denote, and usually U is greater than 0. First, there are two things you need to know, right? It can be U, always capitalized. U can be applied to the ground up loss. In this case, we call U is the maximum covered loss. Okay, this is more likely the default setup for us. So usually when we talk about policy limit, it is applied to the ground up loss. So if you introduce a notation, let's see, X, let's call it XU. Okay, that means this is the minimum between X and U. The mathematical notation is X, wedge, those little triangle, U. Okay, in this case, the policy limit is applied to the ground up loss. Sometimes, or very rare, it's applied to the benefit. This only matters when you have both deductible. So if both D and U are present, and if further U is applied to the benefits, okay, so which means it's applied to the payment. Then, so first of all, we have a notation, okay. We have a different saying. Is right now U is the maximum covered benefit. Okay. Then what we have is I first write it in a piecewise form. So I need to get another page. So let me put it in the next page. Okay. In this case, so let's take a look at the entire. We need. Let's use this notation. So first of all, it will be 0 if your original loss is less than deductible, right? And if it is greater than deductible, but less than equal to u plus d, it will be x minus d. Okay. When it is greater than or equal to u plus d, the maximum. So as you can see from here, the maximum u is actually the payment, right? So the max of this equals u. So the maximum possible payment is u. However, if this is applied to the ground up loss, so let me introduce both. It doesn't go down, so I have to keep this and do another one is if both D and U are present, and if further U is the maximum covered loss, then okay, we have things different. In this case, the first piece is obviously the same. It will be 0 if the original loss is less than the deductible, and it will be x minus d if x is greater than d but less than u. We here the u. And if x is bigger than u, it will be u minus d. So from here, you can see the maximum payment would be u minus d. Okay, that is the difference. Usually, this is the default setup. Okay, but occasionally they can ask you the other setup, right? So when U is the maximum covered benefit, right? The interpretation or the understanding is very straightforward. As you can see here, if this is the case, U is the maximum covered benefit. It is the maximum possible payment from the insurance company, right? If U is applied to the ground up loss and there is a deductible, the maximum payment from the company would be the covered loss, which is U minus the deductible. So that is the difference. Of course, we also studied co-insurance, right? So it is the third one. It is co-insurance. So we have a proportion which is often between 0 and 1. So in that case, the what insurance company needs to take care of is C times X. So this is very easy to handle. The meaning is very straightforward, right? So in this case, you, so let's put a quotation mark. You pay 1 minus C proportion, and the insurer pays C proportion or percentage, okay, of the loss X. Okay, there is the fourth one. It's called the inflation, but inflation is quite different from the other three. Inflation, that is because what percentage we use for inflation? Let's say we use J. Okay, so J is a percentage. So J is actually applied to X. So let's say we need different time scale. Let's say last year, the loss is X, okay? And if you consider inflation, the loss for this year becomes, let's put X tilde. Okay, let me leave some space down here to write X tilde. X tilde equals, let me see. So in this case, we have a new loss. It will be 1 plus J times the original one, right? So that is what information kicks in, right? The size of the loss will go up by percentage J. So basically, this is very similar to, well, it has the same flavor as co-insurance, right? You apply a percentage, but now the percentage is actually bigger than 1. So you can combine inflation with deductible, with policy limit, then the deductible. So if you apply the same deductible D, so effectively your deductible will become smaller. That is because the size of the loss goes up, and if you apply the same deductible, effectively you apply a smaller deductible D tilde. If the original one divided by the inflation, right? The reason is simple. If you apply this, right, you can factor out this this factor, then it becomes X minus D divided by 1 plus J, taking positive, right? So that's something we really need to focus on. And then comes to the main point for today's review is chapter 3, because that is what we, let's put 3. Aggregate loss, and we use S. Again, it can be the aggregate loss for a particular policy or for a group of policies. So the first important one is individual risk model. So let me write down what the model looks like. So here, so all the x's are IID random variables, okay? And we often just use X to represent the distribution of all those ones. And N is positive integer. Okay, the meaning I already explained in the video, right? So small n, you can think it as the total number of policies in your consideration, and xi would be the claim severity of the i's policy. So one, of course, you can interpret it differently, right? I just provide one possible way of understanding, that is n small n. Well, you may think of small n as the total number of policies in the study, and xi is the claim severity of the i's policy. Okay, so that is the setup. Since they are IID, so there are many. There are 2 results that are trivial, right? So mu x is the mean of x, and the variance would be n times sigma x squared. And then, you know, what you want to do is before we calculate probability. So first, let me introduce introduce XII, which is a Bernoulli random variable, okay, to model whether the i's policy results in a claim or not, or maybe claims. So since it's a Bernoulli random variable, we know it's either 0 or 1. Right? 0 means no claim. 1 means there's 1 claim or more than 1 claim. It's up to you to in the modeling. So let's say the probability is theta. Obviously here probability is 1 minus theta. So for each policy, there is a theta percentage for it to result in a positive claim. And of course, we also use Y to denote, so if there's a claim, so we use Y to model severity. So well, you can use yi if you want, okay? But we know because they are all IID, so it's the same thing. So this is an important result, right? Because we use X to model the claim from the ICE policy, and there is a possibility that the ICE policy is a good one. It does not come back with any claim. So it is greater than or equal to 0. Okay, it can be 0. So let me write it. It is possible that X equals 0. Okay. And in fact, that is the most dominant case in pretty much all short-term insurance, right? Let's say if we consider auto policies, those that result in a claim is actually the small part of all the risk pool, right? Otherwise, insurance companies would go bankrupt, or the premium could be crazy. From there, what you usually do is you can apply the Tower rule, right? For instance, this would be when your condition would be the theta times mu y, and the variance of x. Well, you should know this is not E. The symmetrical formula, expectation of conditional variance plus variance of conditional expectation. And when we condition on I, we consider it's either 0 or 1, right? Once you do the analysis, you will get the result is actually you may consider this first. And because I and y are independent, once you take square, they are still independent. And EI square is the same as EI. Right. From here, you can calculate the variance easier. But of course, you can definitely apply this formula. That's what the textbook used, and this is method I prefer you to use. From there, what we do is, of course, we would like to know the actual distribution, right? So previously, we already derived the expectation and variance, but those are not enough to know the exact distribution. So sometimes we would like to know the exact distribution of S, if possible. There are different ways, right? In the textbook, we know they gave the Priel, there's no hyphen, the Priel recursion formula, right? And sometimes you can apply, let's say, probability generating function or moment generating function, or depending on the setup, right? For the probability generating function, the loss severity has to be in discrete values, and if you have a continuous, let me put it. So I think in the textbook we have some examples, right? How if x is continuous, right? We can apply discretization technique to approximate it by a discrete random variable, right? We have example to handle that. Sometimes you can apply, well, like a basic probability analysis to study. This usually works when you want to know the probability of S for smaller numbers, in particular for S being 0. For instance, S equals 0, right? You can analyze, right? S equals 0. If n is 0, obviously yes, right? And then or for n equals this, then all x1, x2, all the way to xn must be 0. And because they are independent, it's the probability raising to the power of n, right? So sometimes you can apply standard probability analysis to do it. We also learned a very important approximation technique, but this is only approximation, okay? Approximation. That is normal approximation. So what you do is, let's say you want to know the probability that your aggregate is less than or equal to some value, small s. So what you can do is you apply normal. Okay, so this is close to a standard normal less than s minus mu s divided by sigma s. Right? This usually will get to the result a lot quicker than any other methods. And if your small n is big enough, usually the approximation is reasonable, if not too accurate. The next one would be the collective. So we study collective risk model. So first, let me give you the model details of deductible of collective risk model. Right. The meanings are straightforward. N is the claim frequency, and xi is simply the ith claim. It is the ith claim, not the claim from the ith policy, because the ith policy may come back clean. Right here we collect. So the meaning of collect is really to collect the. Of course, there are some assumptions, right? Actually, there are two assumptions. Let me write it down. The assumptions we handle are xi's are IID, and xi's and n are independent. So those two will always be assumed when we have a collective risk model. By the way, sometimes we also call this compound risk model. Or we can simply say the aggregate is given by a compound model. Compound model is collective model, okay? And here, the true meaning of collective, the meaning of this word is we collect policies that result in claims or in claim. So that is the meaning, right? Previously, in the individual risk model, we don't make any collection, right? We study all policies from 1 to small n. Those are all the policies in our risk pool. We study the claim information from each of them. Now, under the collective risk model, we only collect policies that result in claims, meaning if a policy comes back clean, we simply discard this policy because it does not require us to make any payment, right? So that is the most important difference between collective and the individual. And because we collect, each xi must be strictly greater than 0, right? If xi is equal to 0, we don't collect it, right? We discard it. So that is a huge difference. All the xi's are strictly positive claims. So of course there are many things we need to know, right? For instance, if you know the probability generating function of n and x, they are given by Pn and Px, then you would know the probability generating function of S is nothing but the composite of Pn and Px, right? And similarly, if you know the moment generating function of n and x, they are n, and nx, then the moment generating function of your aggregate would be the composite of mn with, okay, now it is the log of mx. Okay, from there, there are many wonderful properties from the, for instance, if you want to know if we want to calculate the probability of S at some small value, that is means the aggregate, let's put this to know it's big S, we can apply this function. We differentiate S times and evaluate 0 divided by S factorial, right? That is a useful formula if you want to compute the probability of your aggregate. Again, in this case, we need to assume X takes discrete values, right? Otherwise, the definition of PGF falls down, right? We only have probability generating function when the random variable in consideration takes discrete values, right? So when you have continuous, you study the MGF. Okay, from MGF, you can easily get the expectation to any power of you want, right? To the case power if you want, which means you can differentiate to get the first moment and then differentiate again, get the second moment. Once you know the first and the second moments, you can easily calculate the variance, right? But here we have a very important result. So again, the first one, let me first erase this. This is the end result. So the first one is what we always call the power rule. So once you make this condition, you kind of assume the big N is fixed. Once big N is fixed, we know this is N times mu X, right? Because you are summing up N random variables of X, and they have the same expectation, which is mu X, and is N of them. That's why inside the bracket is N times mu X. And finally, when you take the outside expectation, you regard N back as a random variable. So it's mu N times mu X, okay? We also have the unconditional variance. Again, it's in symmetrical formula. So apply the same idea. For the inside part, it's a conditional variance. It's kind of, you fix big N as a constant. If you fix it that way, it becomes N times the variance of X, right? Because you have N of them, they are independent. Okay, and study the variance. The inside part we already handled is N times mu of X, right? And then when you consider the outside expectation or outside variance, you regard N back as a random variable. In this case, this is a constant, right? So it will be mu N times sigma X squared. And this is also a constant. We study the variance. But the thing is, this constant has to be squared because now we study variance. All right, so that is the very important formula. Similarly, we also want to know the exact distribution, right? But now basically everything is the same, except that now what we have here is Panya, right? Instead of Debria, we have Panya recursive formula. But again, in order to apply Panya, N has to be from AB0 class. So it will be one of the 4 distributions we studied in chapter 1. So basically, I think those are good for us, right? For the review part, I will stop here for the review.